In this topic, we will be covering generator fundamentals including generator theory and induced voltage. We will also cover AC generators including stationary field AC generator, rotating field generator, three-phase AC generator design and operation. In addition to that, we will talk about generator excitation and its major components. Let's talk firstly about generator theory. A rotating generator rotor will produce electrical voltage if three things are present: magnetic field, conductor, and relative motion between the two. Alternating current, AC, generators use electromagnetic induction to convert mechanical energy into electrical energy. Electromagnetic induction is defined as the generation of an electromotive force in a closed circuit by a varying magnetic flux, flow, through the circuit. A basic AC generator is made up of a rotor and a stator. The rotor is a rotating iron core coil connected to a direct current, DC, power source, while the stator is a stationary coil of wire also wound on a metal core. When DC voltage is supplied to the rotor, a magnetic flux is created around a magnetic circuit. This magnetic circuit consists of rotor coil, stator coil, and the air gap between their cores. In this explanation, the top of the rotor coil is a north pole, and the bottom is a south pole. The actual polarity of the field around the rotor depends on the direction of the current supplied to the rotor and on the construction of the rotor coil. Relative motion is achieved as the rotor turns inside the stator. One cycle of an alternate sine wave voltage is produced for each complete revolution of the rotor. Induced voltage in the coil increases as the rotor turns toward the coil. The induced voltage is proportional to the variation of flux which is perpendicular to the stator coil. In our example, the maximum positive voltage will be reached when the north pole is at alpha is equal to 90 degrees where the maximum positive flux variation is reached. When alpha is equal to 270 degrees, the induced voltage will reach its maximum negative value. As the rotor completes its rotation around the inside of the stator, the induced voltage in the stator coil decreases until it reaches zero. Generators may be classified as stationary or rotating field generators, depending on where the DC is applied. In a stationary field AC generator, DC is applied to the stator. The field does not rotate. The rotor consists of a closed electric circuit that rotates inside the stator. The resulting power output is taken from the rotor by an arrangement of slip rings and brushes. A slip ring is connected to each end of the rotating loop. Carbon brushes make sliding electrical contact with the slip rings. The generator's AC output voltage is transferred from the slip rings, through the brushes, to an external circuit. It is difficult and expensive to build and maintain slip rings and brushes to carry large amounts of current. Therefore, stationary field AC generators are used in applications which involve small amounts of power. Most large AC generators are rotating field generators. In a rotating field AC generator, slip rings and brushes are used to carry only the DC which is needed to create the magnetic field. This is significantly less than the generator's AC output. Most AC generators are designed and built to produce three-phase AC because of its size's compact size, and a better efficiency is reached with such an arrangement. In a three-phase AC generator, three sets of coils are arranged in the stator 120 degrees apart physically. Three voltages are generated simultaneously, but the maximum value of induced voltage in each coil occurs 120 degrees apart electrically. Generators usually operate at a frequency of either 60 Hz or 50 Hz, 60 or 50 full cycles of AC per second. To supply power at a constant frequency, the rotor has to turn at a constant speed. Rotational speed in an AC generator depends upon the frequency and the number of poles in the generator field. In a simplified three-phase, four-pole AC generator, there are two north poles and two south poles. An AC cycle is produced when a north pole and a south pole pass a coil. To create the magnetic field required, DC is usually supplied to the rotor winding by an external source, called an exciter. Depending on the generator type, two of the most used excitation system types are brushless or static. Both perform the same function and are shown in symbolic form on the figures in the corresponding paragraph. In a brushless excitation system, excitation is supplied by a rotating armature machine coupled to the generator shaft. The machine has a three-phase winding in the rotor and a DC field winding in the stator. In a brushless excitation system, excitation is supplied by a rotating armature machine coupled to the generator shaft. The machine has a three-phase winding in the rotor and a DC field winding in the stator. AC from the three-phase winding is rectified in a rotating three-phase diode bridge, rotor, and DC is fed to the generator field winding, which are also in the rotor. The exciter's DC stator winding is supplied from the generator terminals through an excitation transformer and rectifier. The voltage regulator electronic circuits are also supplied from the generator terminals. Modern large generators usually are not equipped with rotating exciters, and the required excitation for the generator field is provided directly by a controlled rectifier bridge fed from the generator terminals through an excitation transformer. The ceiling voltage required for the generator rotor can be selected through the ratio of the excitation transformer. The main advantage of static excitation is the response time for sudden increase or decrease of excitation current. The permanent magnet AC generator, PMG, provides the power to the voltage regulator. The regulator then compares the operator's voltage set point with the output signal at the generator stator terminals. Once processed, the regulator's output signal is input to an AC to DC converter. Finally, the DC output is used as the input for the main exciter's stationary field winding. The AVR controls the amount of current flowing from the PMG to the stator of the main exciter. It rectifies the AC voltage coming from the PMG into DC, which it supplied to the field of the main exciter. The amount of current supplied to the main exciter field determines the output of the main exciter, and thus regulates the generator's voltage output. The following paragraphs build on information already presented on the design and operation of the AC generator and its excitation system to explain how generator voltage is regulated on a continuous basis. The field of an AC generator basically consists of an iron core coil which rotates at synchronous speed inside a stationary armature. When current enters the slip rings, it flows through coils embedded in slots in the rotor and produces a magnetic flux with a north pole and a south pole. This rotating flux, which induces stator voltages, flows through the field core, across the air gap, around the iron armature punchings, back into the field core. Voltage is induced when lines of magnetic flux flow perpendicularly through a conductor. In the generator design we are discussing, voltage is produced when coils in the slots of the stator are affected by the rotating magnetic flux. The amount of voltage induced is a function of three conditions: flux density, which is the number of magnetic flux lines per a certain area. Second condition is rotor speed, which determines the flux variation. And last condition is conductor length, which means the length of the machine and the number of coils in series with each other. Under normal operating conditions, synchronous generators run at constant rated speed. The geometric arrangement of rotor and stator windings is fixed by its design. Hence, the only way to change voltage during synchronous operation is to change the density of the rotating flux. This is accomplished by changing the generator's field current. With the generator main breaker open, no load condition, stator voltage is a function of the applied field current and speed. As field current increases in an open circuit condition, stator voltage increases. This relationship is linear up to the point at which core saturation takes place. Core saturation changes the reluctance of the magnetic circuit. Reluctance in magnetic flux circuits corresponds to resistance in electrical resistance circuits. As field current increases, flux density increases, and the iron circuit becomes further saturated. It means when the flux density reaches a certain value, the relationship between field current and produced flux is no longer linear. The more the circuit is saturated, the more field current is required to change stator voltage. When the generator is connected to the grid, stator current will flow and a different flux distribution will exist. The amplitude of the terminal voltage is proportional to the air gap value. Just one part of the field current will flow through the magnetizing reactance. Air gap voltage and stator voltage are no longer equal because of the voltage drop. In conclusion, in on-load condition the stator voltage is a function of speed, excitation current and load connected to the stator terminals. Explanation of armature reaction, need for change in field current. This flux field rotates around the stator at synchronous speed. The field acts in such a way that it distorts the flux produced by the field current in the rotor and changes the number of flux lines crossing the air gap and linking the armature coils. This is known as armature reaction. If field current were to remain unchanged, stator terminal voltage would change with variations in generator stator current or reaction. The density of the stator reaction flux is a function of the amount of stator current. More stator current results in a change in both the resulting field and stator terminal voltage for a given value of field current. In order to maintain the desired stator or terminal voltage, the field current must be continually adjusted to produce the same number of flux lines crossing the air gap and linking the armature coils. In other words, the field current required at load is a function of the field current required to produce rated voltage at no load, plus an additional amount to overcome or cancel out the effects of armature reaction. As already noted, excitation power requirements are small when expressed as a percentage of the generator rating. Field current is important because it determines generator terminal voltage, reactive power flow from the machine, and the ability of the machine to remain in synchronism with the system to which it is connected. The extent to which field current determines generator terminal voltage depends on system loads and the relative size of the generator. The AVR component of the excitation system monitors generator output voltage to determine the strength of DC amperage applied to the main exciter windings. If generator output voltage changes, the AVR increases or decreases the flow of DC to the main exciter windings. This produces a change in the main exciter's AC voltage and current output, which is sent to the rotating rectifier. The rotating rectifier converts the main exciter's AC output to DC, which is directed to the generator field windings. Generator output voltage is increased or decreased by changing the current supply, number of flux lines, to the generator. That brings us to the end of this topic today. In next video, we will be discussing about air-cooled generator design and major components. Please like and subscribe us for further training video. Thank you for your watching and see you then.